So in this video, which I suspect will finally be the last for the stochastic processes playlist, we'll be looking at ergodic theory and stationary processes. I think I talked about ergodic processes or ergodic theory rather in when I was talking about dynamical systems. So you want to check that out. Okay. So we move on to ergodic theory and stationary processes. And this lesson covers stationarity, whether it is strict stationarity or weak stationarity, ergodicity and long-run averages, autocorrelation and spectral analysis. And we look at some applications in time series analysis, signal processing, and econometrics. So straight up to stationarity. A stationary process, a stochastic process, X, which is a collection of variables X indexed by time, right? Is stationary if if its statistical properties do not change over time, right? So, and then we have the idea of strict stationarity. So a process is strictly stationary if xt1, xt2, up to xtn uh, is equal to xt1 plus h, xt2 plus h, xtn plus h for all t1 up to tn and any shift h. This means the entire distribution is invariant under the time shift. That means xt1 is the same thing as xt1 plus h. So the shift h does not make any difference, right? Xt2 is still same as xt2 plus h. Xtn is the same thing as xtn plus h. So shifting doesn't make any difference. So that is strict stationarity. This means the entire distribution is invariant under time shifts. Now, when we come to weak stationarity, then we say a process is weakly stationary if it has a constant mean, right? The expected value of x of t is always mu, no matter what the time step is, right? So that's weak stationarity. Then it has constant variance. That is variance of x of t at any value of t is sigma squared always. And then covariance depends only on lag. So the covariance of x sub t comma x sub t plus h is equal to gamma of h. So it's a function of of h. So we can then talk about the example of white noise. So let x sub t be identical and independently distributed with mean zero and variance sigma squared. Then we say the mean, of course, is zero, variance is sigma squared. And because the mean is zero, then there's no autocorrelation. So this process is strictly stationary and it's also weakly stationary. So then we can visualize this, right? By, just taking, we do seeding to maintain the same result over time. So if we take 500 steps and we look at some random values from 0 to 1, like that, we want to check white noise under that and want to see what the mean will be and the variance would be under those values. So this is mean of the distribution right here. So, so imagine what we have here. So for this one, and the mean is minus 0.025 and variance is 0.99. That's close to 1. So, and the reason why this is not changing is because we have this random seed. So if you don't want to, if you want it to keep changing, you can just comment out this and you see that each time you run it, you get a separate result. So you can see this minus 0.06 for mean, 90.029, variance is 0.93. Now mean is 0 minus 0.0019, variance is 0.9426. Now it keeps changing like this. But if you want a stable value, so you can do the seeding thing, and then so this way you are guaranteed that although it is a random thing, but as far each time you run it, you get the same result. Now, this is random seed zero. For most of my work, I use seed 42. I think I need to. Okay, now with 42, it's now like this. So the seeding you want determines on this is dependent on the uh the kind of results you actually want to show will determine the seeding. If I do 21, for instance, so we get something slightly different. So, but because of that random seed thing, we keep having the same results, you know, as far as we have that line 4 there, we have the same results. But if you change the seed, you have another result, but you have it constantly. That's the beauty of the seed. Okay, so we go to ergodicity. Okay, ergodicity, the basic idea of ergodicity, I think it follows something like the law of large numbers. It's something close to that. So ergodicity connects time averages and ensemble averages. So it's saying that if you toss a coin, if you toss a single coin 1,000 times, So the result, the average value you get is it will equal to the average value you get when you toss 1,000 coins at once. So ergodicity connects time averages and ensemble averages. So, and it is simply summarized in the fact that the limit of 1 over t summation from t equals 1 to t of xt as t tends to infinity is the expected value of x of t. So if this holds, then we say the process is ergodic. So this is simply saying, so this one is like when you toss a coin, it like 1,000 times, it's equal to the expected value of x 100, like that. So if this holds, the process is ergodic. So in that case, we can then say that, okay, I mean, why does ergodicity matter actually? In practice, we observe only one realization of a process, right? And not many independent samples. That is actually in practice. But ergodicity then allows time average to be approximately equal to expectation. So something that you take over time, that you average over time, is equal to whatever exactly the expected value might be. Okay? So now, for example, now we have an ergodic process like white noise. So we have white noise as an exact ergodic process. We have time averages converging to mean. So for a non-ergodic process now, x of t will be equal to z, where z is a random constant, right? So each realization is constant. So time averages differ across realizations. Okay, so that's a non-ergodic process. So for a non-ergodic process, the each realization is constant, and then time averages differ across realizations. So we have this situation here. So we have um, random seed of 1 here. So if I run this now, we have the true mean. So this is actually the true mean, but so it's more like the expected value when you toss a coin, of course, whether you get head or tail is 0.5, for instance. Of course, this one is not about coin, but so if you now toss one coin 1 million times, for instance, so you have values very close to the actual mean. So in this case now, the true mean is 5.0, and then the so for the other, the one that you're doing over time, so it sees flow. So at first it's like it's hovering around the mean, and then later it goes above it, and then it's getting closer and closer to it as you increase that. So what if I make it like 10,000? It gets uh closer, closer, closer. Now you can see it's almost aligning here, you know. So the more so it reminds me of the law of large numbers, that the more samples you have, the more the value you get is close to the real value. So let's talk about autocorrelation in this case. Autocorrelation at lag h. So you have rho of h to be gamma of h over gamma of 0. So where gamma of h is the covariance of xt, comma xt plus h, right? So in this case now, this will be covariance. So what gamma of h will be covariance of xt plus h, whereas gamma of 0 will be covariance of xt, comma xt. So xt and xt, like that. So the interpretation is that rho of h equals 1 means perfect correlation. Rho of h equals 0 means no dependence. That is, whatever variables you're considering, xt and xt plus h or whatever, do not have anything in common. Then rho of h less than 0 implies inverse relationship. So taking an example of autocorrelation 1. So an AR1 process is defined an AR1 process is defined by x of t equals phi x of t minus 1 plus var epsilon of t. So where the current value depends on the previous value scaled by phi. So xt depends on xt minus 1, but it is scaled by phi. Plus, you now have a random noise term. So this is a random noise term, epsilon sub t. So the parameter phi determines how strongly past values influence the present. So if it is 1, so it means that xt minus 1 perfectly determines xt, right? So if it is close to 0, it means that xt minus 1 is weak in determining what xt would be. So the autocorrelation function ACF is given as rho of h, which is phi raised to power h. That is this coefficient raised to power h, the lag, which means autocorrelation decays exponentially with lag h. So when the absolute value of phi is less than 1, so that means minus 1 is less than phi is less than 1. So that means phi lies between minus 1 and 1. The influence of past values diminishes over time. So recent observations have the strongest effect, like that. Okay, so we can also demonstrate that using, I mean, the idea of autocorrelation here, taking 500 steps and we take phi to be 0 0.8. So in fact, we can play with the phi and see how it goes. And this one determines the AR1 process, for instance, XT. So this determines the AR1 process. You have XT equals multiplied by X minus 1 plus noise at time T. So it gives, this values you see right here. So so this is, what if I take phi to be 1, for instance? Phi is 1. So phi is 1, so you have something that high up there. What if I take phi to be 0.1, So you have this kind of thing. So the current state is weak in determining the next state. That's actually what this is about. So let me make it something even like smaller, 0.01. Okay, so same. So, but if it's like 0 0.9 or even 1, so you see that the determination of the next one is as close as can be, like that. Okay, so that's what autocorrelation function is about. So let's talk about spectral analysis, which is one application of this ergodicity and everything. So spectral analysis studies signals in the frequency domain. Interestingly, I have a playlist on spectral analysis. So if you're interested in signals or even so you can also see data, right? Data, you can see data as signal, in spectral analysis. So spectral analysis can actually be useful in data analysis, actually. So spectral analysis studies signals in the frequency domain. So the spectral density is given as S of F, which is summation from H equals minus infinity to infinity of gamma of H e raised by minus I to pi F H. Of course, we've seen that gamma of H is actually the covariance, yeah? It's actually the covariance, so which helps us to compute autocorrelation like that. So we have that. The interpretation here is that low frequencies implies long-term trends, right? And high frequencies talks about rapid fluctuations. So an example would be when x sub t is 2 sine 2 pi ft plus epsilon sub t. So spectral density shows a peak at frequency f. So you have a peak at frequency f. So, and here now, imagine fs is 100, and then you have, of course, if you check the spectral density playlist, spectral analysis playlist, you learn a lot about periodogram and all of these kind of terms attached to signal analysis. So here now, we just set up the system. You have 2 pi 10t, f here is 10 now, and then you have the noise component here, like that. So, and if you run that, you have this power spectral density. So I talked a lot about power spectral density too in this spectral analysis place. Let me even show that to you. So just click here, go to YouTube, and of course look for my name, right? It's my channel. So here now you have go on playlist and then you find spectral analysis. Spectral analysis, where is that now? Um, okay, so it's been a while. Interesting. Spectral analysis. I think it's still more recent than all these ones. Yeah, it should be close to real analysis playlist. Spectral analysis. Spectral analysis. Okay, I think it's more recent. Oh, okay. Oh, yeah, right here. Because I remember I did it concurrently with the real analysis playlist. So here you learn a lot about the different terms, of spectral analysis. So like that. Um, I want to, okay, so look at this now. Introduction to spectral analysis, the periodogram, power spectral density, and all these terms like that. So if you're interested in signal processing, you want to definitely check out spectral analysis like that. Okay. Now, so this is the power spectral density right here. Then we talk about some applications. Okay, spectral analysis. Yeah, we talk about some applications of ergodic theory and stationarity and stationary processes, right? Ergodic theory and stationary processes. Some applications, ergodic theory and stationary processes are widely used in time series analysis, signal processing, and econometrics. Then for time series analysis, for instance, so the workflow will be something like you want to, for if you have a time series, you test for stationarity, and from there you transform if needed, and then you fit the model to say ARIMA or SARIMA, or there are all kinds of models, and then you can validate the residuals. So a very good example of that will be this now. So we want to carry out a kind of ADF test here. So from the start model, you need the ADF fuller, and then you take the ADF statistic and get p-value. So you run this now. So this p-value is very small. So that means that whatever you have here is statistically significant. So signal processing now. For signal processing, you have applications in noise filtering, frequency detection, communications, and of course, signal analysis is central in this area of signal processing. And then when you go to econometrics, you have things like you have ergodic theory and stationary processes used in GDP modeling, inflation analysis, financial time series. Then stationarity ensures valid statistical inference. So stationarity, the fact that things don't keep changing can help you to actually make decisions, right? But when it keeps changing, and that's why we do seeding also, when we have to deal with random situations. So we have a financial example right here. So talking about financial returns, imagine that R sub t is log pt minus log pt minus 1. That's like p of financial return RT is the log of time at price at time t minus the log of time at a step before time t. That's time t minus 1. So here you see if we say prices are stationary, non-stationary, and returns are often stationary, right? So here now, imagine we have prices here. So we have the prices to be NP dot cumulative sum of NP dot random normal. So between 0 and 1, we take 500 plus 100, which is like basic. And then we have the returns. NP, that it's more like you're differentiating the NP dot log prices, and then you plot the returns, and then you have your log returns here like this. Okay. So that's the idea. And of course, that would keep changing except you set a seed, like we usually will do. But so you see, this one keeps shifting shape like this. So in summary, in short, we have stationarity. The meaning of stationarity is that it is statistical properties. You want to stationarity means that statistical properties are constant. Strict stationarity means full distribution is invariant, that no change in time does not affect anything. So it's more like what we say in dynamical systems, that something has reached equilibrium, that no matter what you do, it doesn't change. Then we have weak stationarity where mean and covariance are stable. Then for ergodicity, you have time average equals expectation. So the expectation of a coin uh, is the same thing as what you get. The expectation of tossing a head or tail for a coin is the same thing you get when you toss a coin several times and you average it over that time. That's the basic idea of ergodicity. And for autocorrelation, that talks about dependence over time. And spectral analysis talks about frequency decomposition. So it's more like breaking a signal into its various components. So, and then we have some practice problems, and I'm going to answer questions 3 and 6 here. So, for stationarity, determine whether the process xt equals 5 plus epsilon sub t is weakly stationary, where epsilon of t is IID with mean 0 and variance 1. So, it's related to the thing what we've done before. Check if the process xt is t plus epsilon t is stationary, explain why or not. Show that white noise is weakly stationary. I'm going to answer this. Then, is the process xt equals cos t plus var epsilon of t stationary sub t? Justify your answer. For x sub t equals phi x sub t minus 1 plus var epsilon t, state the condition on phi for stationarity. Then you talk about ergodicity now. So I'm going to answer question 6 also. Explain in your own words what it means for a process to be ergodic. Then show that white noise is ergodic in mean, right? Then consider x sub t equals 0, where z is normally distributed with mean 0 and variance 1. Is this process ergodic? Then compute the time average. That's 1 over t summation from t equals 1 to big T of x sub t for a simulated white noise process and compare with its expected value. Then give an example of a process that is stationary but not ergodic. So, for autocorrelation, define the autocovariance function y of h and explain its significance, compute the autocorrelation function for white noise. For an AR1 process, this derive rho of one. I mean, we did that before. Then we have if phi is 0.5, compute rho of 2. Then explain how the autocorrelation function helps identify model structure. And then you have the last set of questions here. So for spectral analysis, what is the relationship between autocovariance and spectral density? Explain what a peak in the spectral density indicates. For the signal x of t equals sine 2 pi ft, what do you expect the spectrum to look like? Well, we know f plays a significant role. Then applications, why is stationarity important in econometric modeling? Explain why financial returns are often modeled as stationary, while prices are not. Okay, so maybe for better decision making. So, like I promised, I'm going to answer questions 3 and 5 and 6 rather. I know the question 3, I think that one is about white noise. Question 3 is about white noise. Let's go for them right away. So I go to the worksheet so I can do that there. So for three, question three says, uh, want to show that white noise, that is white noise is weakly stationary. Okay. So here now we say let x sub t be a white noise such that x sub t is identical and independently distributed with mean zero and variance sigma squared. So to prove weak stationarity, right? To prove weak stationarity, we check the three conditions. We check the three conditions. Okay, the first condition, of course, for weak stationarity, the first condition is constant mean. Constant mean. Okay, that's the first condition for weak stationarity. And we know that in this case now for white noise that has mean zero, the expected value of x of t is equal to 0 for any kind of t, for all t. So the mean is constant at 0 there. Then 2, constant variance. You have constant variance. So for constant variance, you have variance of x of t equals sigma squared for all t also, because that's what the distribution tells us in essence. So variance is sigma squared, so for all t. Then number 3 now, we want to check autocovariance. Autocovariance depends only on lag. Okay, so here now for h not equal to 0, if there's no lag, so we know that gamma of h is equal to covariance of xt plus h, and that is equal to 0, you know. So then for h equals 0, we know that gamma of 0 would be variance x of t, which is always sigma squared. So thus we know that gamma of h can be described as the step function, which is sigma squared when h is 0 and 0 when h is not equal to 0. So now we see that um, this depends on the lag of h, on the lag h rather. This depends on the lag h, not on time t, not on time t. Okay, so We can then say, therefore, white noise, white noise satisfies satisfies all conditions, all conditions of weak stationarity, weak stationarity. Okay, that's about question 3. So let's also take care of question 6. So this is question 3, right? This is question 3. Okay, okay, this is question 3 now. Let's go for question 6. So question 6, it says explain, explain in your own words, what it means, what it means for a process, for a process to be ergodic, to be ergodic. Okay, so we go for that now. So we say that a stochastic process is ergodic, is ergodic if it's long run, if its long run time, if its long run time averages, its long run time averages are equal to its theoretical, to its theoretical, to its theoretical, or what you can call the ensemble, or the ensemble averages. And a very good example is that of a coin that you know the the expected value for tossing what that you get a head or tail when you get toss a coin is 0.5. So the ergodic part now is the long run time averages. In that case, if you have like 1,000 tosses, 1 million tosses, so the average will always move towards that the theoretical expected value of 0.5. So mathematically, mathematically, we see that that can be described as the limit as t tends to infinity for 1 over t, for 1 over t summation t equals 1 to t x sub t, and that is equal to the expected value of x sub t, basically. So this is the long run average and this is the theoretical average. Okay, so with that in place now, the interpretation, right? We can talk about the interpretation. Interpretation. So, first of all, if if we observe, if we observe a single, if we observe a single realization, if we observe a single realization of the process over a long time, over a long time, we can we can estimate it. We can estimate it. We can estimate its expected value. We can estimate its expected value. Then another point is that we do not need multiple independent samples, multiple independent samples. Because of the ergodic theory, right? If you already know the theoretical value, you don't need multiple independent samples because as you move closer and closer, you're going to get to the expected value. So the process explores all possible states, all possible states over time. Okay, so in simple terms, right? In simple terms, in simple terms, we say that time averages, time averages is equal to population averages. Time averages is equal to population averages. Then we also see that one long observation is enough to understand the system. It's enough to understand the system. All right. Then example, right? Example. We just talked about white noise in question 3. White noise, white noise is ergodic. White noise is ergodic because averaging averaging over time, averaging over time converges to its mean. Okay. And then we can talk about a counter example. Counter example. So for the counter example, right? If x sub t, a stochastic process equals z, which is actually a constant random variable, a constant random variable. Okay. Then each realization is constant. Each realization is constant. That's one. Then another thing is that time average. So the time average will be that constant. Time average is that constant, right? That constant. So time average is that constant. Then but expected. So on the other hand, for ergodic theory, right, expected value differs across realizations. Across realizations. Okay. So in that case now, we know that we can say so xt equals z is not ergodic. And on that note, we come to the end of this interesting video on ergodic theory and stationary processes. So again, I'll flash the questions so you can try your hands on them. So question 1 to 5 talk about stationarity. Question 9 to 10 talk about ergodicity. Question 10 to 15 talk about autocorrelation. And 16 to 18 talk about spectral analysis. And 19 and 20 talk about application. So try your hands on this and let me see how well you understand these concepts. If you let me know if there's something else you like on the tryouts. If you have subscribed already, I thank you very much for doing that. If you have not subscribed, of course, you want to definitely do that because you don't want to miss out on anything that is going on this channel. So if you have not subscribed, just click on the subscribe button, and of course, also click um on the alert on the bell so you can always get alerted each time a new video is released. After that, you can also become a member of this channel, and that gives you special privileges like getting to see some videos first or getting to see some videos exclusively as members of the channel. You can also request for PDF copies of my notes. We can hang out physically if you're in the same geographical location at any point in time. We can also hang out online to talk about anything that interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, or any such things. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.